Good afternoon, everyone, and welcome to today's sponsored ABC webinar, Beyond Initial Cost, Exploring the Full Life Cycle of Biogas. My name is Caroline Pete, and I will be facilitating this webinar. And before we begin, I want to give a big thank you to today's sponsor, Mayekawa, for sponsoring today's webinar. Their sponsorship directly supports ABC in our program, so thank you very much appreciate it. Before we get into our content today, just a bit of housekeeping. First, you should be able to hear me, and you should see the slide entitled Quick Notes. If you're hearing echoes or your sound quality is bad, you can change your audio options in the GoToWebinar toolbar on the right side of your screen. And if you're still having trouble, you can send the organizers a message also in that GoToWebinar toolbar using the questions pod, and we will help you get through those. And if you still miss it past that, we are recording the webinar and we will send that to you by the end of the week. If you have any questions about the content today, we also encourage you to use that questions pod. Ask your questions at any time whenever you have them. Our questions will be handled in a Q&A period at the end of the content. And with that, I'm going to hand things off to our moderator today, ABC's Executive Director, Patrick Surface, to lead you through today's presentation. Patrick, please take it away.
Great, thank you so much, Caroline. Thank you again to Mayekawa for sponsoring today's webinar. Today we are going to be talking about compressors. So, we've got about 2,400 operational biogas systems all around the US. And unless you're upgrading the gas to an amine system, if you are going to membrane to clean up your gas, going to PSAs, going to engines, microturbines, fuel cells, linear generators, all of those things, you're going to need to take the biogas that comes out of your system, whether it's coming out of a landfill or coming out of a digester. You're going to need to take that biogas and compress it so you can do other useful things with it. And that's what we're going to be focusing on with Mayekawa, because that's the focus of their business, is how do you size your compressor correctly? How do you know how to operate it efficiently? How do you make sure that it's going to be working for you, and why their equipment over any other competitors? So we're really excited to be able to dive into this with them. Carlos, we're really excited to have you and hear from you today. And with that, I'm going to let you introduce yourself and your company further. I know you guys have been around for a long time and been supporting the ABC, which we appreciate. And hand it over to you. Thanks, Carlos.
Okay, thank you, Patrick. Thank you so much. Thank you, everybody, for being here today, listening to me a little bit about exploring the full life cycle of a biogas. My name is Carlos Falsiroli. I'm Mayekawa sales manager for oil and gas and chemical division here in USA. I'm responsible for Mayekawa business development in USA. My background, I'm now 20 years or 30 years of experience in the same sector, always in compressors. And I got an MBA from University of Toronto, and also I am certified with strategy and global business from Harvard School. A little bit about myself. My background is engineering. I'm an electronic engineer. I joined Mayekawa here in USA in May 2021. So thank you so much for being here today. Next. Yeah, I need to talk a little bit about Mayekawa. Mayekawa is a Japanese company. This company was founded in 1924. So we have 100 years of experience in the compression business. We are a leading manufacturer of industrial compressors, no matter it's for industrial refrigeration or process gas, oil and gas, or biogas. And we excel when talking about reliability and how to provide value to our customers, reducing downturn and energy efficiency, even for industrial refrigeration or any other cooling or oil and gas, process gas, or process refrigeration. So we cover a lot of a broad range of applications all over the globe, with more than 100,000 screw compressors installed worldwide. Next. So yeah, a little bit about the network, talking about Mayekawa. This is not a small company. We have a global footprint, total revenues around $1.7 billion. Mayekawa being headquartered in Japan, but we are present in 43 countries with 103 offices around the globe and 7 production plants where we have these hubs for packaging and manufacturing compressors. One important thing is we have in Mexico a facility in Cuernavaca where we also manufacture screw compressors. And South Korea, we have a packaging company. We assemble the systems in South Korea, in Serbia, also in India, Chennai plant. In Belgium, we concentrate our operations in Europe, in Belgium, or we call the Mayekawa Europe. And USA, we are basically located here in Katy, Texas, in the greater Houston. Another important plant that we have, the global footprint, is in Brazil, with a big plant in Brazil to cover all over South America. So it's a little bit, you see, we are very well organized around the globe to support our customers, no matter it is industrial refrigeration, biogas, or process gas. Next. So the agenda for today, I want to talk a little bit about the biogas treatment process. What are the mainly process where we have applications for screw compressors. I'm going to talk a little bit, what is the importance of the screw compressor in this treatment process. Then I expect to talk a little bit of theory of the screw compressors, how the twin screw compressors, oil fluid machines, they work, exactly the compression process, and why it is important when selecting a compressor, look for some parameters to have a better efficiency. And then I talk specifically when selecting a compressor, what is the compressor efficiency? How we can optimize efficiency? How we can have a better output with the lower input of energy, saving money to our customers and adding value to our customers. And then I talk about the reliability points, specifically to the biogas application. What are the main constraints on the biogas when selecting screw compressors from the material point of view and the design of the screw compressor point of view? And then I'm going to talk about the total cost of ownership. Along a period of 7 years, how much it's going to cost to have a screw compressor in your biogas facility, in your biomethane facility. Next. So next. So the biogas treatment process basically starts from you produce the biogas from organic waste in a digester, in an anaerobic digester. And these digesters will have a set of anaerobic bacteria that will digest the organic matter, not breathing oxygen. So the result of this breathing is going to be mainly methane, CO2, and some other gases in a small percentage like H2S, water, water vapor, nitrogen, and oxygen in small amounts. The big issue here, in order to inject this biogas into the pipeline, you need to treat the biogas and changing it to biomethane. So you start after the digester, you have a pre-treatment biogas where you can remove some components that are not desirable for the compression stage, like the H2S, some water content, nitrogen, siloxanes, or other volatile organic compounds that are not good for the compression. So we try making a pre-treatment up to a point where you're going to go to a membrane or a PSA. This is one type of a biogas upgrading system. And I'm going to talk about membrane or PSA because you need compression for these systems. So the membrane or PSA, they separate the CO2 from the methane, and higher the pressure in the membrane is the better the separation process. So that's why in these systems you have there's a need for a high compression ratios, and I'll talk about how to optimize efficiency from high compression ratios and having a better separation system of membrane through this high compression ratio. After we upgrade the membrane, upgrade the biogas from the membrane, you have the biomethane and the bio-CO2. In the biomethane, you inject the biogas into the pipeline, or you can also liquefy in some cases the methane into liquid methane. We also can provide refrigeration systems for methane liquefaction, or also you also separate the CO2, have the bio CO2, and also can have you might need, if you don't dispose the CO2 to the atmosphere, you might need the CO2 compressor either to compress your system or to a liquefaction system. And also Mayekawa can provide the CO2 compressors for your system, because we also have the refrigeration systems and CO2 compressors for those systems. Next. So how exactly a screw compressor work? Let's talk a little bit, to understand the theory of the screw compressors. Next. So screw compressors, they are positive displacement machines. So this means that those machines, they increase the pressure by reducing the volume of a specific gas. Basically, in a screw compressor, we have two rotors in a helical shape. One rotor is the male rotor, and the other rotor is the female rotor. So between the male rotor and the female rotor, you have gaps, spaces, where you fill these gaps with a specific gas that you might need to compress, or you want to compress. So when the rotors turn, the gas enters to the rotors from the suction port, and then you fill those gaps between the male and female rotor up to a point where you seal the gas between the rotors and the casing. When the rotors continue to turn, then you start to squeeze the gas, or reducing the volume, increasing the pressure. So the rotors, the lobes, they mesh from the suction side, and these interlobe spaces, they decrease, increasing the pressure of the gas up to a point where the gas reaches the discharge port. So the amount of gas that you're suctioning and the amount of gas, there's a relationship between the amount of gas that you're suctioning and the amount of gas that we are discharging. This relationship, we call them the volume intern ratio. All screw compressors, they have the same principle. All screw compressors, they have what we call the volume intern ratio, or the VI. Every single machine has this feature, and the efficiency will depend very much how you select the proper VI for any specific application. There are no suction valves or discharge valves like in reciprocating machines. You just have the gas entering through the suction side, squeezing the gas, compressing, and going to the discharge port with no valves retaining the gas within the rotors. Next. So basically, you see the relationship. The VI, or the volume intern ratio, is the relationship between the volume that is suctioning immediately before to start to compress the gas, and the volume of the gas that's pushed out to the discharge port. So this you can see here in the figure. You have the gas go inside the chamber up to a point where you seal the gas and starts to reduce the volume, and then you discharge the gas into the discharge port. So the compression ratio is also a relationship of the volume ratio. The compression ratio is the volume ratio power to the kappa value, which is a specific feature of any specific gas. The kappa value is the adiabatic coefficient, which is a relationship between the specific heat at a constant pressure divided by the specific heat at a constant volume. So basically, when you select a specific VI, you are selecting a specific compression ratio for this type of gas. Next. So that's a figure showing here. If you look on this, you see exactly the compression when the rotor turns, right? So if you look in the figure on the left, you see the low VI conditions, which means you have a higher suction pressure, the rotor turns, and you start to squeeze the gas up to a point where the gas reaches the system pressure, right? So When you have a low compression ratio, you have a low VI. That means the discharge port is bigger because you need a big volume for a low VI ratio. In the second figure, going to the right, you see a high VI ratio. You see you need a small port, discharge port, because then you have a high VI ratio, which means a high compression ratio. So look into this, you see that the gas, when the gas reaches the discharge port, they're going to meet the system pressure. If you're selecting a very low VI for a high compression ratio to the system pressure ratio, what's happened, you see in the figure 3, you're going to see overcompressing, undercompressing. The gas will return to the rotors and then you need to recompress again. So you see the gray area here on the third figure to the right, you see this additional energy they're going to spend to recompress the gas that is turning back to the rotors. On the other hand, if your compression ratio is too high, then when the gas reaches the discharge pressure, it's going to re-expand. So then you also have to, you are spending additional energy to compress more than you need. So also you're going to spend more energy. So it's important when selecting a compressor, try to matching or optimize the volume ratio to the system compression ratio, which means you're optimizing your internal compression ratio, the screw compressor internal compression ratio to the system pressure ratio. If you mismatch this relationship, you're going to spend a lot of energy. Next. So that's you see you are under compressing, you have the gas returning to the discharge side of the compressor, so you need to recompress this gas and you spend more energy. Next. Or if you are compressing more than you need, the gas, when it reaches the discharge port, will re-expand, meeting the system pressure. Next. So how you control the capacity of these Mayekawa screw compressors is what I call a slide valve. A slide valve is a valve on the bottom of the screw compressors where you shorten or make the rotors longer. So you see in the figure that when you open this slide valve, you are reducing the volume that you are displacing because you are making the rotor shorter. In the right side of the figure, you see the unload conditions. You see the slide valve moving onto the left side, means that you are shortening the rotor, so means that leading to a lower volume displacement, so you can control the capacity through controlling the slide valve. The slide valve is basically controlled by a hydraulic piston, where you inject oil into one side of this piston, on the other side, based on the control decision on the pressure, the suction pressure or the discharge pressure. So then you can optimize the volume displacement based on your need, the system need. And also, our machines, you have a very high turn down, no need to recycle, because you can go up to a minimum of 20% of the compressor capacity. So when you don't need, for example, the compressor at 100%, is, for example, membranes, you cannot start the compressor loading the membranes immediately. You need to unload the machines to build up the pressure in a smooth ramp. So then you can unload with the slide valve and start moving the slide valve to load position and building up the pressure slowly. Next. So this is a general overview about how the oil fluid machines work, especially our oil machines work. You see the rotors. We have three main oil lines. The blue line is where we feed we inject oil for the bearings and for the seals. Our machines, they use sleeve type radial bearings and roller types thrust bearings or tilting path thrust bearings. This means that we have force feed lubrication systems with the external oil pump. The reason for that is because we increase a lot the reliability of the systems. So the blue line means you have the oil injection for the bearings and for the seals. The yellow line is the orange line, is for injection of oil. You inject oil in the rotors in case that you need to control the discharge temperature. There are cases that you need to reduce the discharge temperature. so you can additionally inject oil into the rotors. And one line, line 3, is the hydraulic control for the slide valve. So the hydraulic control for the slide valve is basically you have a control where you sense the pressure, can be on the suction side of the machine or the discharge side of the machine, and then you take a decision whether you need more capacity or less capacity. So the control will inject oil on one side of the unloader piston, or on the other side loading the capacity, the slide valve and the compressor. Then you can modulate the capacity as per the process need. Next. So, as I said before, in order to optimize the compressor efficiency, it's important to have a look when you have a system to match the VI as much as we can, so then we can optimize the power consumption. And I will show a little bit some examples I will give you 3 examples, and I'll talk later in the sequence. Next. So I have selected 3 cases to analyze the power consumption of a screw compressor. In this case, a Mayekawa screw compressor. Right? So we have the case 1, what we call the ideal case, when you have a matching VI. The case 2 is a single stage machine with a mismatching VI. And the case 3 is optimizing the compression ratio through a compound system, or in a double stage system. So imagine the case 1, you have a biogas with a suction pressure of 14.7 psia and a discharge pressure of 145 psia. The suction temperature is 90 degrees Fahrenheit, and the system compression ratio is 9.86 to 1. Why? Because you divide the discharge pressure 145 by 14.7, and then you have 9.86 to 1 compression ratio. So I need to select a compressor with a VI that must match the system compression ratio. In Mayekawa, we have a VI, a single stage compressor with a VI of 5.8. If you make a calculation of this compression ratio, 5.8 powered by kappa value, you're gonna have 9.83. So this is exactly matching the VI. Can you see the next? Is you see any? Can you put next to see? Yeah. So in this case that you have matching VI in case 1, the absorbed power is going to be 811 horsepower, which means very low horsepower, because you are efficiently compressing the gas, matching the compressor ratio to the system pressure ratio with the optimized VI. But now imagine that you're going to operate in a membrane system where you change the discharge pressure, and this is the case 2, from 145 to 350. So now the compression ratio, the system compression ratio, is 23.8 to 1. But we're still using the same compressor from the case 1, where the internal compression ratio is 9.83 to 1. So you see now the absorbed power is going to be 2,251 horsepower vis-a-vis 811 horsepower from the first case. We don't have a compressor, or many fuel manufacturers, they do have a compressor with a system ratio of 23.8. This is going to give us a VI of 11, if I'm not mistaken, around 11. You can just make a calculation. You can power 9.83 to the kappa value, and you're going to give you the theoretical or a matching VI ratio of a screw compressor. It's very uncommon any compressor manufacturer have this VI ratio. So what do we do next? So what we do, we have what we call a compound machine, which is a double stage machine in just one frame, which means you only need one compressor for a double stage machine, and then you rationalize the VIs per stage. So even though it's not perfect, you are optimizing the VI ratio. So now, optimizing the VI ratio, the absorbed power on case 3 is 1,127 horsepower, which is even a little bit higher than the ideal case, but a half of the mismatching single case, case 2. Next. So optimizing compression ratios plays an extremely important role in the total cost of ownership, because the biogas upgraders, they are selling energy. So lower the energy input for selling the same amount of energy is going to make more money. You have your cash flow, additional money in terms of business performance, right? Next. There are other points to consider when analyzing the screw compressors for biogas application. Next. So we need to take in consideration for the biogas composition. The biogas composition, in its majority, we have 50 to 70% of methane, 25 to 50% of carbon dioxide, nitrogen, hydrogen, traces of H2S. We have saturated water. We have ammonia in the gas composition. So look into the biogas composition. It plays a major factor when selecting a suitable screw compressor. There are many points in the design of the screw compressor that can guarantee the reliability. The CO2 content also must be analyzed, and we need to try to avoid condensation during the compression, because this can cause oil dilution, this can cause acid formation. Water with the CO2 can cause the formation of a carbonic acid, which is corrosive, right? You need to analyze the dew point of any water content to avoid any kind of dilution and causing problems in the bearings, for example, reducing the span of maintenance span of the machine. Some machines, if you have this issue, you need to open the machine within 1 year or less. In our case, we recommend to open the machine to make inspection only after 3 years time. So the reliability is very long. H2S and CO2 along water can form carbonic acid or sulfuric acids, and some materials are not compatible with this kind of acids. So we need to have special materials to avoid any kind of problems and guarantee the reliability. And the bearing lifetimes is really depending upon all those points. So you can have bearings failing very frequently if you don't pay attention to these factors. It's not simple. You select a bearing, for example, the radial bearings, the anti-friction radial bearings for this type of conditions, they cannot have a long lifetime. So that's why in our designs we have anti-friction bearings. We have sleeve type bearings with oil film between the bearings. The tilting pad thrust bearings also, they must guarantee the thrust forces of the system, because you can have problems in terms of reliability of the thrust bearings. The other thing is there are lots of variation in the gas composition during the operation, and this may lead to reliability issues. So maybe you can have, when you select the screw compressors, we have one condition, we analyze this screw compressor for conditions, but the anaerobic digestion is not very constant depending on the type of bacteria that you have in your digesters. So the variation in the gas composition can also lead to problems into the screw compressors if you don't select a proper compressor for your operation. I want to ask you if you have some questions at this point of the presentation. Okay.
Carlos, I see that there's one question here about the energy use of the screw compressor. I saw that you had a ratio there of energy use, but can you describe a little bit more how much energy your compressors need?
Yeah, so we can go back to
as a percent of biogas production. Okay.
Yes, if you can go back to that slide about the table showing the different yes. So if you look in the case 2, a mismatch in single stage, you have a power consumption per volume flow of 0.85 horsepower per SCFM, right? In the case of the optimizing with the compound machine, you have 0.39 horsepower per SCFM. Adiabatic efficiencies of a case 3 optimized compound is going to be around 75 to 78%. And case 2, if you mismatch, you know, the theory is the same. The thermodynamics is not going to change depending from one machine to another. If you're going to work in a mismatch, the adiabatic efficiency is going to be very low, around 50%. So that's why you see the differences in the power consumption, right? I don't know if I answered your question, but
we're getting some more in. Do you want to take more questions now, or keep going and take more at the end?
Yeah. Next. Yeah, other point you need to pay attention in the biogas is the water content in the gas upstream the compressor. So I have here a case showing a biogas composition of 60% of methane, 30% of CO2, 1% of nitrogen, 1% of hydrogen, 3% of H2S, 4% of water, and 1% of ammonia. If you look on this, with a suction pressure of 14.7, discharge pressure of 350 psia, suction temperature of 90 degrees Fahrenheit, sorry, it's a PSA was Fahrenheit, you're going to have a relative humidity of 84%. So if you look here on the right side of the calculation, with 84% of relative humidity, the dew point of water at the discharge is going to be 201.7 Fahrenheit. And the compressor discharge temperature is going to be 232.5 degrees Fahrenheit. We need to guarantee a minimum superheat discharge to avoid the condensation of the water content into the during the compression. This is a critical point because if you have condensation, then you're going to have liquid formation and carbonic acid formation, oil dilution, and corrosion problems into the machine. You look that in the graph. Can you next? So this means that if your discharge temperature is lower than 201.7 Fahrenheit, you have condensation of the water in the gas stream. So then you're going to start losing bearings, oil dilution, you lose viscosity of the oil. Then it's going to cause problems into the system, right? So you need to force the temperature up to avoid condensation. So forcing the temperature up also force additional forces into the compressor, thermal expansion of the rotors, problems in the seals, problems in the bearings. So sometimes it's better to avoid water coming into the system to guarantee the reliability of the overall system. Next. So you see, you need to keep some superheat between the discharge temperature and the dew point of the water. And the amount of water into the system and the relative humidity is something that is going to play an important role when selecting the screw compressor for the biogas application, biogas feed application. Next. So some takeaways from the water content. High relative humidity demands high discharge temperature. So minimum 30 degrees Fahrenheit of superheat to the dew point to avoid water condensation. And again, when you force the discharge temperature to go very high, then again, you have other things happening inside the compressor. Axial forces are higher, thermal expansions are higher, rotor deflections are higher. So you need to select proper materials for that. Water condensation causes oil dilution, which affects the compressor's reliability and quality of compressed gas. Other thing is if you have water condensation with the CO2 and H2S, you have corrosion because there's a formation of carbonic acid and also sulfuric acid. We need to check the thrust bearings because to guarantee the compressor reliability, because there are problems in the oil dilution, there are problems of thrust forces, high thrust forces, and this can cause reliability issues into the compressor. The discharge temperature, the compressor discharge temperature must be below the critical point of thermal expansion. Otherwise, you can have rotors touching the casings, because the clearances of these compressors are very, very small, right? And also, you increase the thrust forces. You need to redesign the thrust bearings. In our case, when you see that happening for every single case, we select tilting path thrust bearings to guarantee the reliability. And also, we have balanced piston, where we design oversized balanced pistons to compensate the additional thrust forces through the thermal expansion. And of course, we need to take careful consideration of the HUS content, because if you're using a cast iron machine casing or nodular cast iron machine, the HUS can cause a sulfide stress cracking, can cause embrittlement of the material, and the material can break apart very easily. So it is not proper to use cast iron or nodular cast iron when there's HUS content into the gas composition going to the compressor. Next. Next. So basically what I mean is that we need to guarantee a minimum superheat when you have water content of 30 degrees Fahrenheit to avoid water condensation. Next. So some examples about material compatibility, right? So cast steel, if you have sour gases like HUS, you can use cast steel. Put next, please. So we can use cast steel, we can use corrosion resistant cast steel. You cannot use cast iron. Nodular cast iron can be used under some conditions. However, it's not recommended. And also molybdenum, chromium molybdenum steel forgings are not recommended, which means you need to have a special regard about the material compatibility when selecting the screw compressors for biogas technologies to avoid sulfide stress cracking or machine corrosion. And in some cases, some end users are not paying attention to that and sacrificing the operation, having machines breaking down and having production stopped because of this lack of attention to the materials compatibility. Next. So look a little bit the compound machine, a double stage compressor, Mayekawa solution, what we call the C series. You see that in the design, you have two rotors. One, the big one's the first stage, and the second one is the smaller one's the second stage. The thrust bearings we have, they are roller bearings or tilting path thrust bearings, which means ball bearings or tilting path thrust bearings, which means they support the axial loads to the gas forces. The compressor is the screws, the rotors, they are helical, so they are geared. So also when they turn, they have forces. Then we have force on discharge side and the suction side. So to offload these forces, we have these thrust bearings, a face-to-face ball bearings or tilting path thrust bearings, and also we have what we call the balance piston. The balance piston reduces the gas load received by the thrust bearing. So this will increase the reliability of the bearings in the machine. This is made by hydraulic pressure in opposite direction. The radial bearings, they support the gas load in the radial direction using the oil pressure. So in this case, we don't have roller bearings. We have unfriction bearings, hydrodynamic bearings, which means you need external oil pump to keep the oil film between the shaft and the bearings. So this will optimize and increase a lot the reliability of the bearings, avoiding to stop the machine very often. So we recommend to stop the machine after 3 years of operation. And we can provide mechanical seals in many different types. We can provide single stage seals, double stage seals, API piping plant seals. We can provide plant 52 unpressurized wet seals or pressurized wet seals, plant 53 or dry seals if the customers they desire this kind of solution. Next. So talking about the total cost of ownership, going back to that slide, let's talk about the total cost in 7 years. How much is going to cost a compressor in 7 years? Next. So next. So in this, we have some premises in here in this consideration. We are talking about the total cost of ownership in the mismatching single stage or optimizing compound. We are considering here the cost of capital, 8%, the energy price, 5 cents of dollar per kilowatt hour, and the maintenance cost, $30,000 from starting on year 3. This is when, in case of Mayekawa, we're going to start to looking performing maintenance in our machines. So in a mismatching case, single stage, the capex of buying a system is $700,000, and the energy cost is going to be $3.7 million if you consider 7 years the horsepower that we saw in the previous slide, and the maintenance cost is going to be $120,000. So the total is we have $4.6 million. So the energy total cost is 82% of the total cost of ownership in a period of 7 years. If you look on the compound, you have a little bit higher capex because the machine, basically we have 2 compressors in series with 1 motor. We are considering $950,000, but the energy cost, because of the power consumption is much lower, is $1.9 million in 7 years, and the maintenance cost also is going to be lower because you're going to stop the machine less. So in total, we have $2.9 million of total cost of ownership. How we make this calculation? This is a stream of cash flows in 7 years, and we brought this value to a net present value with a cost of capital of 80%. This is what we have done, right? So if you want to check the calculations, you need the calculations, I can send a spreadsheet for you guys later on showing the overall calculations. Next. So this is just a graph showing what is relevant in the total cost of ownership. Energy is super important. It accounts for 82% of the total cost of ownership. And of course, you know, from the operational point of view, if you have less input and maximum output, it's gonna give you a better return on investment if you consider the maintenance cost in the total value of in the total cost of ownership. Next. So again, you know, looking at the capex, you're spending in capex additional $250,000, but in 7 years you are saving $1.7 million of maintenance and energy costs, providing higher, more efficient power flow and better results in terms of cash flow and better return on investment. Right? Next. Next. So just showing a little bit of comparison about the single stage machine, mismatching single stage, or a double stage machine with just 1 motor. So we try to optimize the capex because in a double stage, in our case, you just need 1 motor, and the motor is a heavy component of the total cost of the system, right? Next. So talking about our line of products, you have a broad range of products. We have what we call the SCV series, or more standard machines with cast iron casings, not very much flexibility in terms of design, but this is more for industrial refrigeration. The J series have what I call the automatic variable VI. We can change the VI automatically depending on the operating conditions. And the UG series, these are the machines that you're using for oil and gas and biogas. These machines, they have a broad range of different materials. We can use those machines in casings made of a cast iron, hardware cast iron, cast steel, low temperature cast steel, different rotors, forged steel rotors, different bearings, tilting path thrust bearings, or ball bearings, or slip tight radial bearings. We use this for biogas. The G8 series are high pressure machine. The 360 GV, we launched these machines last year. Those machines, they don't use hydrodynamic bearings, it's the radial bearings. They are roller bearings. In the C series, these are the compound machines. They are more efficient for high compression ratios, in line with the UG series and different materials of casings and rotors and different seals and bearings. So these are very flexible machines for the biogas market. We can go with the C series and UG series, can go up to 10,000 CFM in terms of volume flow. So they're big machines, maximum power around 4,000 horsepower. So next. So some conclusions. So energy cost accounts for approximately 80% of the total cost of undershift. And Mayekawa can offer excellent solution with the C series, a double stage system with just one motor. Next. The compression ratio is higher than 12:1 leads to a double stage system if you want to become efficient in terms of power consumption. Next. The gas composition, pressure, and temperature analysis is crucial in customizing optimal and reliable compressors. If you want a safe operation, you need to look the overall gas composition, operating conditions, and select the right machine for your application. You're just not selecting a screw compressor without analyzing the design of the bare compressor or design of the system design, because otherwise you can be jeopardizing the overall operation, having this machine stopped by very, very often. So it's important to have a look on these factors as well. Next. Water content and dew point temperature must be analyzed for gas quality, materials, and reliability to avoid corrosion, to avoid condensation, and keep the machine in the safe region, the compressor in a safe region of operation. Next. And then finally, Mayekawa can help you to find the perfect custom screw compressor for the biogas treatment you need. We have different machines and different solutions. Depending on the application, we're going to have the right solution for you using different materials, different designs, a tailor-made solution as per your need. Next. So a little bit about Mayekawa maintenance across North America. This is where we have our service center. We have service and spare parts located in Torrance, California, Seattle in Washington State, in Vancouver, British Columbia in Canada, Calgary in Canada, in York, Pennsylvania, USA, in Toronto in Canada, in Springdale in Arkansas, and also in Houston. We have a different facility where we service our machines. Next. And I hope the presentation was good. I hope I could bring some insights for you guys, and hope to see you guys in Biogas Americas on April 28 to 30 in the Colorado Convention Center. We're going to be there. So hope to talk to you a little bit more details if you are there. Thank you so much. Questions for me?
Thanks, Carlos. Yeah, there's a lot of questions. You can tell the folks online are really engaged here. So let's just power through them. I've got almost a dozen here. So let's just get started. And for those of you who haven't written your question in the questions pod, you can see the directions there on how to do that. So are the compressors controlled with suction control or discharge pressure control?
You can do both. You can control, depends on your philosophy, but you can control the capacity through discharge pressure or through the suction pressure. Both ways it's possible to control. Depending on the upgrader, in some cases the upgrader, they prefer to control from the suction pressure is the most common cases.
A lot of questions here on maintenance. So let's see if I can do a good job of grouping them all together. What's the normal amount of time lost per year for preventative maintenance?
Well, we recommend our maintenance. We recommend after 3 years we start to inspect only the machines, right? So you open the seals and the bearings, and you inspect the conditions of these components. You're going to spend like a maximum 2 days to perform these inspections. The main overhaul that's going to take around 5 days is after 5 years of operation.
And so you said 2 days a year, I think, and then 5 days once every 5 years or so. What's the total amount of expected downtime for preventative maintenance or other maintenance that your customers should expect?
Well, in 7 years, we are talking about total amount of time. 10 years is gonna be 7 to 8 days in 7 years.
Okay. So about yeah, around a couple days a year, basically.
Yeah.
Great. What about for the life expectancy of the compressors?
30 years total life expectancy of the compressor.
Okay. What's the best way to manage the noise for the compressors? What do you recommend for your customers?
Well, there are some ways to manage the noise. One of them, you can put a blanket in the compressor to minimize the noise. And the selection is also important. You know, the matching the VI is something important because those machines, they produce pulsation, right? If you have mismatching VI, you have additional pulsation that can increase the noise a lot. So first thing is the selection. To minimize the noise, you make a proper selection. Second is select the correct oil, because oil also has a function to minimize the noise. And even though if you cannot minimize so much the noise with those criteria, then you can insert a blanket into compressor or have some acoustic hood to minimize the noise.
All right, one more maintenance question for you here. What are the costs for major maintenance, like when you have to do a rebuild for like the single stage versus the compound machine?
That's a good question. I don't have this answer right now, but I can check. I can check and send later on.
All right, and then the last one is what's the domestic content for your system? Do you know that requirement with the Inflation Reduction Act?
Yes, we can comply with the Inflation Reduction Act. Now we are achieving 70% of local content with the existing designs. We have supplied already systems with in compliance with the Inflation Reduction Act, because we only bring the screw compressor from Japan. All other components they are procured here in USA and assembled here in USA. So let's say we are in full compliance with the Inflation Reduction Act right now.
That's great, and what a great note to end on. Carlos, thank you so much for sharing all your knowledge with us about your compressor systems. Looks like a goodbye to me. And yeah, thank you all for attending today. I think you'll probably get a link to a survey after you close the webinar here after we shut things down. And Caroline, unless you have anything else, I think that's it.
Thank you, everyone.
Thank you so much.